Hello class, welcome to this lecture. So today we're going to be talking about solving stiff ordinary differential equations. So in practice, when you're working on these really big problems, pretty much all of your equations are going to be stiff. Why is that the case? Well, we can show, and we'll probably show later in this course, that partial differential equations give a form of stiffness, right? So for example, diffusions, constants, result in a time span in which, it results in a time span that some particle can move from one box to the next, right? When you're looking at a spatial simulation. And if you're allowing particles to move one box at a time, then if you move too fast or you forget about some effects, then you have this kind of stiffness effect of not, going beyond the time scale at which your model is kind of written to do one step at a time for. Um, there's other effects in there that cause stiffness as well. So anything with timescale separation, which are the things that you generally want to simulate, like biological systems or pharmacology, chemical reaction networks, combustion, batteries. All these things have a lot of timescale separations because you have these small processes that build up over time to then give the macro process. And that's the thing that a lot of times you're trying to understand, right? How do the small effects of a material give rise to the aggregate design? If it just kind of was something simple like, how do these five things interact? That's something that we kind of know how to do pretty easily these days. But how do these million things give an emergent property of acting like a liquid or acting like a solid? That's something that's really hard to understand just analytically. And this is what we're using a lot of computational simulation for, and that by design is going to be something that is a stiff differential equation, right? So how do we handle stiff differential equations? So last time we saw that, the problem with stiff differential equations, right? When you have which the problem of stiff differential equations is that you have this property that you have very large eigenvalues, right? That's how we can define it. In reality, the way that you define it is that you have a large eigenvalue and a small eigenvalue. Technically, you define it on the pseudospectra, but that's really related to the eigenvalues. So, to a first approximation, you can think about it as based off of the eigenvalues and the eigenspectra instead of the pseudospectra. Uh, but if you don't know what the pseudospectra is, just it kind of ignore it. It's just based off of small perturbations. Um, so the idea there is that you have a fast time scale and a slow time scale, right? So you have the fast wobbles and you have the slow arc. And what you want to do is you want to resolve the slow arc while not letting the fast time scale throw you off, right? So we saw this example last time of if you do the little squiggles and you kind of estimate the derivative at a given point, it tells you that you're going to be going all the way up here in half a second, but that's because that really large derivative only exists for a little tiny amount of dt, and so you don't want to overestimate. You don't want to let that affect your estimation, right? You got to somehow average over larger time scales, and that's essentially what implicit methods kind of let you do, right? They're kind of averaging things out by being an integral over a given space instead of being an extrapolation. Right, so they're really trying to solve that in that. I mean, ordinary differential equations are an integral, right? They're an implicit integral. And what these implicit methods are trying to do is they're trying to average out the quantities by directly approximating that integral by solving the implicit equation that it defines every single step, right? Um, so what you essentially get from these methods, right? So you translate from being able to use what you have now. You put f in, that tells you the next thing, right? To put f in, get the next thing, right? That's the Runge-Kutta method. Um, and you lose the niceties of the Runge-Kutta method, and now you have to solve a fully implicit equation. So you've now said, I need to use an implicit equation in order to satisfy these stability bounds, right? Because if I use an explicit method, if I have my largest dt is blah, which is based off of the fast time scale, which means I can only simulate, I can only do dt of picoseconds when I need to go to milliseconds, right? So if you stick to that, you have to do 10 to the 7. You need to do a million times that. It's just not going to happen, right? Well, you need a lot more than that for that case, but so what you want to do is you want to then replace it with one of these implicit methods. Why? Well, because that allows you to handle the fast eigenvalue, and that allows you to use times. It allows you to handle the fast time eigenvalue, but take DTs on the time scale of the slow eigenvalue, right? And so that's why people say it's all about timescale separation, right? So you might think at first that it's all about just the largest eigenvalue, but if all you cared about was the largest eigenvalue, then the time scale, I mean the time scale that the system is moving matches the eigenvalues, right? Um, that's what we saw from the analytical solutions to the linear ODE, right? The time scale that something moves is like e to the eigenvalue on the eigenvector, right? So, so if you had only fast systems, you would only need to solve it for a very short amount of time to resolve the fast system and like see its entire dynamics, right? It would either start repeating or would start being on a chaotic attractor, or it's going to go to a steady state, right? And in the time scale, which is on the time scale of that eigenvalue, maybe like e to that eigenvalue, 2 or something, right? It will have already done its period. It will have already gotten so close to the steady state you can no longer resolve it in float 64, right? And so the problem that we have is that the moment you have a slow time scale where you want to see the large scale behavior and a fast time scale which restricts your time step, those two pieces together makes you want to move to one of these implicit methods. So how do you actually do the implicit method efficiently enough that it is not slower than actually just doing a million times, right? Because a million time steps is easy. Right? We showed how to optimize that. So if you are working with unoptimized code, using a million time steps could probably even be a bit faster than just doing, just a very naive implicit method. And you could probably easily see this. That's actually why we've omitted a homework problem along this, because it takes a lot of time to engineer something for implicit equation or implicit solvers. But what we're going to go through today is exactly how these implicit solvers in production senses, how they're made. Again, we're not going to be writing one from scratch here because that is a lot more work. The explicit OD solver will be your homework problem, but the implicit OD solver is something that is much more expansive in its work. So what we'll do here today is mostly just describe all of the ways that it's used, and we'll see that there's a strong story, a strong connection with automatic differentiation that comes into play when implementing and working with these methods. So let's get started on that, right? And so everything that we're going to be talking about today is just with the implicit Euler method. But all of the other methods, adaptive BDF methods like LSODA or CVODE, all of these methods kind of have the same core to them. Like it doesn't matter which implicit solver you kind of use other than a fully implicit circuit. So Radow is different slightly. Radow still ends up at a very similar problem, but it's slightly different. Um, Anything like these ES-Stirk methods, Rosenbrock methods, anything like CVODE, LSODA, the whole list of things that you probably use in practice, ODE15S, ODE23S, right? They all end up with this same system. And I'll point to it right here. It's basically this system with, instead of DT, you get like an alpha in front of it, right? Some constant. But you end up in the same place. Um, and you might add a constant value, a constant with respect to un plus one there, but it's this same exact equation. So by understanding how things are done on the implicit Euler method, this is the core to all the other ones. Um, so okay, what is the implicit Euler method, right? So we looked last time and we said, okay, it is the approximation where you know where you are, you calculate a derivative, and you move forward delta t by the derivative, right? The derivative is f, that's given to you by the ODE definition. Where do you evaluate f? Explicit Euler means you evaluate f at your current spot. Implicit Euler is where you evaluate f at the future, right? So here it is right here. Implicit Euler is the method where you take your current spot and you move forward in delta t by an approximation of the derivative. But here, the approximation of the derivative uses the future point, right? So the point in the future, the point in the future. So, okay, if we wanted to use this method, we need to find un plus 1. So in order to find un plus 1, if in very few cases, like if f is linear, you can actually solve directly for what un plus 1 is. But in almost every case, you can't, right? So what do you do instead? Well, you move everything to one side, which this should be looking a bit like your homework, right? But you move everything to one side, un plus 1 minus delta tf of everything minus un equals 0. And now you have a problem. G of un plus 1 equals 0, right? Why do I not include un in this function? Well, because we're assuming that we're at un and we're making the step to un plus 1. So un is already a constant. So un is constant, and so this is really just a function of you've already chosen delta t. You've already chosen you already know un. You're what all you're trying to calculate in this problem is un plus 1. So, okay, so this is a classic root finding problem. So what you want to do is you want to find, we have a function g of x, and we want to find the x such that g of x equals 0. So, okay, so how do we want to solve this kind of system? Well, what we do is we replace the root finding problem by a discrete dynamical system whose steady state solution is g of x, right? Or g of x equals 0. And what's the method that does this? Well, we saw from the homework, right, that there's two of them, right? You can use fixed point iteration with this white twist, along with Newton's method, right? These are both methods that will give you a root of an equation. So what we need to do is we do need to make sure that the root finding method itself is stable, which was exactly the homework problem, and trying to understand what are the ways to be able to stabilize it, right? So what you should have found in your homework was that when there are these different types of methods that are very similar, they do have different stability, right? So then the stability here is when will they converge to the root? So for example, you can have fixed point iteration, which is the same thing as instead of using the Jacobian inverse here, you can instead just use minus the identity. And when you do that, you can show that it's going to be less stable than something like a quasi-Newton method, or less stable than a relaxed Newton method or a relaxed quasi-Newton method, right? So in this problem, we do see that when you have a very stiff system, you do need to use at least a quasi-Newton method in order to solve it efficiently, in a way that is able to handle the stiffness, right? Because if you have a very stiff equation, then having really large eigenvalues is exactly the case where using I instead of the Jacobian will lead to a system whose its eigenvalues are going to be out of control, and so you have to be very close to the steady state to begin with in order for this to actually work, right? Which is kind of infeasible. um, so you could make that happen. We'll see exactly how. It turns out that case is the case of exactly making dt small again. So what we're going to need to do is we're going to need to make sure that we're using a very stable root finding method, which means we have to be able to be far away from our solution to start with, and then allow that to be able to converge in a nice way, even when the eigenvalues of the Jacobian are very ill conditioned. So you have very large eigenvalues and very small eigenvalues in there. Um, you can there is another method that does exist. So there is Anderson acceleration. I'm not going to explain that in full here. You can go look it up if you want. I mean, the paper that introduces Anderson acceleration is very accessible, so I would recommend you go read it. There's nothing about the stability of the method in there, but we know from practice, both in developing the differential equation solvers in Julia and the developers of sundials, we've both noticed that Anderson acceleration is a method which is more stable than fixed point iteration, but generally not as stable as quasi-Newton, so everything still tends to default to quasi-Newton, even though Anderson acceleration doesn't require Jacobian calculation. So we're going to stick with quasi-Newton or Newton methods because Newton methods are by far the most common way to handle these implicit problems that show up in stiff dynamics. So let's use the syntax g of x equals 0. Um, we need yeah. So when I refer to this g of x equals 0, this is the problem that we want to solve, right? Where this g is the left hand side of this equation. So we need some starting value for this root finding problem, right? We need some starting value for what x would be. Remember that x is supposed to become un plus 1. There are many ways to kind of look at how you should do this. So, for example, you can say, well, so you have a system already. You've already solved a little bit, And when you're right here, you can say, well, I can use the previous point and the point before that, draw a line, stick the line out, make it push the line forward. Where would that line hit in delta t? That could be my best guess for un plus 1. You can make a polynomial of previous terms, quadratic, quartic. You can go as high order as you want. Make the past four terms give you a polynomial, extrapolate that polynomial out by another delta t. How well does that do? All these methods are people that use things that people use in practice, though the easiest and actually kind of the most stable is to just guess that un plus 1 will be equal to un, right? Why might you not want to work too hard on the prediction? Well, I mean, you might want to do something simple, like maybe linear or such, but if you try to guess too hard, remember that it is the extrapolation property that is something that is highly ill-conditioned here, right? Um, like when you just try to use a derivative and just push forward, right? That's the thing that causes the stiff and the non-stiff method to go unstable, right? So you don't generally want to do a fifth order polynomial and then just use its approximation, because that's one of those things that can blow up in extreme stiffness. Um, so a lot of times people use the guess of un plus 1 equals un. There are much smarter guesses that you can do, especially in second stages and third stages and stuff. And a lot of the engineering within stiff ODE solvers goes into this guess. It's also something that we're looking into more for research projects, because it is actually very crucial to how efficient the implementation is. But the easiest guess is to say this should say un. So the easiest guess is just to say un plus 1 will be equal to un. So that means that my starting point is x0 equals un, and then I want to solve Newton's method to kind of bring it all the way up to un plus 1. Right. So once we have a starting value, we run the iteration. Right. What is this iteration? Well, this is Newton's method. Right. So we take xk, we evaluate g on it, we evaluate the Jacobian of g on it, we take the inverse of the Jacobian of g, we multiply it to g, we subtract it from xk, that gives us xk plus 1, right? And your homework is all about analysis of this exact iteration process. So this is a discrete dynamical system. We know it converges under good conditions to the root finding solution. We know how stable it is. We know what causes instability. We feel good about this, right? So the mathematical formulation is not the syntax, though, that you would actually use in an application, right? In general, you pretty much never want to calculate the inverse of a matrix. Even if the Jacobian is sparse, right? Most of the time, your Jacobian of your differential equation is sparse because you don't have every single term showing up in every other term. There are counterexamples to that. The neural ODE is a major counterexample to that. But instead, what you normally want, so you never want to invert a matrix, because even if that matrix is sparse, its inverse is still likely to be dense. So that means, if the full matrix doesn't fit in memory, so you use a sparse matrix representation, trying to calculate the inverse of it will run out of memory, right? So you never want to do that. While this is what Newton's method looks like on a piece of paper, it's not what it looks like in a computer. So how do you do Newton's method on a computer? Well, you do it in 2 steps. So this right here, right? So remember that right. So the first thing that we want to look at is basically J A equals G of xk, right? Well, what we could do here is we solve for A. So A equals J inverse G of xk. And what do you know? J inverse G of xk is exactly what we wanted here, right? So instead of calculating an inverse, what we want to do is we want to solve this linear system. And there are ways to solve this linear system which do not require calculating the inverse of a matrix. And that's some of what we'll go into. Then the next thing is, after you calculate A, then you just do the update equation using A, right? So the core to this problem of doing Newton's method is actually solving a linear equation, where the linear equation is defined by the matrix that's in your linear equation is J. Right hand side is just an application of the right hand side of of the root finding function. So just a quick note here, right? So what is the Jacobian of G? What is the Jacobian of yeah, so what's the Jacobian of G? Let's write it out. So we have G of X equals we have X minus, delta T. Let's see, do I do that? Yeah, so I'm gonna just change dt into gamma, where gamma is some function of dt, and this is how we actually do every method, right? So with Euler's method, gamma equals dt. With trapezoidal method, gamma equals half of dt. With Ken-Carp 5, gamma equals 53 over 442. It's like it's one of those optimized Tableau coefficients that goes here, multiplied by gamma. So it always ends up being something multiplied by gamma, and so we could just say it's always going to be some function of delta t. The fact that it is a function of delta t is crucial here, and we'll see in a sec. But so okay, so I'm just gonna write it down as being a gamma. So we're gonna say gamma times f of x, and then p, and then t plus delta t. Right. So to simplify things, I'm just going to, for the sake of this lecture, just say this is a function of x because these other terms are just constants, right? So I mean, you can say I made a closure where I enclosed these other variables. I made this a constant function in the other variables and just made it a one variable function, right? Okay, this is the core of the computation that we're trying to do. And so let's do the multivariable derivative, right? So g prime of x equals, well, what's the derivative of x with respect to x? Well, when x is a vector, remember it's the identity matrix, right? And so what is the derivative of a constant times a function? Well, it's going to be the constant times the Jacobian of the function, right? Same calculation that you did in your homework. So the key here is really that you have I minus gamma times f prime of x. So it's just, so the Jacobian of G is essentially just a function of the Jacobian of your ODE right-hand side. Um, and so this holds true for all the other method forms. So you end up with some kind of g of x that looks like this, and then you end up having to solve some kind of linear systems where this g prime of x, right? So this j is equal g prime of x. Sorry, it's about the notation change there. So g prime of x, this is a matrix, right? This matrix is defined here, which is defined, this exact form, this exact linear system shows up in every single implicit differential equation solver. So it doesn't matter which method we're really talking about at this point. That really just comes down to identifying what gamma is. So there's another detail in here that is very important to kind of know about, right? So when we talk about differential equations, there are some examples of cases where you want to be able to solve something where you have a known conservation law, right? So you have models like, let me pull up the differential equations documentation here. You have models like the following. Notice it's in the stiff equations section. So you have models like the following. So you can say, well, I have dy1 dt equals some differential equation, right? dy2 dt equals some differential equation, and then y1 plus y2 plus y3 equals 1, right? So this is actually an equation that we looked at last time. This is the Robertson equation, or also known as Rober. And in this kind of equation, right, we have a constraint. There is no derivative defined in this part, right? So this is two differential equations with one algebraic condition. So this is known as a differential algebraic equation. And one of the nice ways to handle differential algebraic equations is to handle them as a mass matrix differential equation, right? So we can extend in the realm of implicit ODE solvers, we can extend the types of equations we're looking at to include problems of the form u prime equals mu prime equals f of u, right? Dropping off the other terms. My claim is that this is sufficient to be able to define a ODE with conservation laws like we see on the screen here. So how would you do that? Well, let's look at this, right? So we can, what we need to do is we need to find a matrix here. Okay, so we need a 3 by 3 matrix, which is our mass matrix. The reason why it's called a mass matrix is it shows up very naturally as the mass term inside of finite element discretizations. Um, but here you also can use it for other things. Right? So here, what we want to do is we want to look at the matrix vector notation of this equation. So y1, y2, y3 equals, well, let's write out this equation here. It equals 0 minus 0.04 y1 plus 10 to the 4th y2 y3. Right, that's the first equation. 0.04 y1 minus 10 to the 4th y2 y3. Right, notice the time scale separation is pretty gigantic in this case. Minus 3 times 10 to the 7th y2. And our last equation is y1 plus y2 plus y3. And then there's an equals 1. Well, let's move the equals 1 to this side, right? So it's 0 equals this equation, right? Now let's do the matrix vector multiplication. We need dy dt to show up over here. I'm sorry, this is y1 prime. This is y2 prime. This is y3 prime. Right. So if we want y1 prime equals this, then we do 1, matrix vector notation, it'd be 1, 0, 0, right? We want y2 prime to show up in the second equation, 0, 1, 0. We want 0 to show up on the right-hand side here, so it's just 0, 0, 0. And so actually this encoding, right? So m equals this with f of u equal f of u being the vector of y's equals this is the way to be able to encode that differential equation with a conservation law in there directly into a mass matrix form. So when you have a differential algebraic equation, so one of these equations where you have constraint equations, then your mass matrix is going to be singular. And so it is a function of the form mu prime equals f of u, but you cannot write it as a standard ODE m inverse of f of u because this is a singular mass matrix, right? Um, so you can't do that, right? You have to leave this in the form, but this is an interesting type of equation, right? So here's a question: Could we solve this kind of equation? This implicit differential. Could we solve this equation without ever inverting m? Well, let's actually put it into the Euler method, right? So the Euler method, remember, is where we say m equals delta t or delta u over delta t equals f of u, and so then we move everything around and we get m un plus 1 equals m un minus plus delta t f of u, right? Right. So so yeah, so if we were to keep m inside of this equation, right, because this delta u becomes un plus 1 minus un, then this is what we get, right? So we move everything over, yada yada. Now, if we then look at the implicit system that we get, what we have is m un plus 1. Well, let me write this down correctly. This is the implicit system, right? Which means that, now we have g of x. If we're to define g of x, right, so before we started with g of x equals this, and I just kind of dropped off the constant. So I guess that there is a constant here, and when you take the derivative, the constant falls off. Right? So there is a constant here, and it's a function, and also has an m in front of it. So in this case, we have m times x minus gamma f of x still, right? Plus m times c. And when you take the derivative, right? So when we actually want to do now we want to do Newton's iteration to solve this equation. When we take the derivative, right, g prime of x equals, well, now it's a constant m times x, and we're taking the derivative with respect to x. It's just the constant, right? And then minus gamma um, f prime of x. So here, so before our linear system, right? So the steps to actually do Newton's method are solve this linear system based off of J, and then do an update, solve the linear system, do an update, solve the linear system, do an update, repeat this until you converge, right? Um, where this linear system is based off the Jacobian, generally you have I minus gamma f prime. But if you happen to have a mass matrix, you can solve this without ever inverting m by itself by making g prime, that Jacobian is now just m minus gamma f prime of x. If you use that, then you have to solve a linear system based off of m minus gamma prime, uh, m minus gamma f prime, right? But notice that this matrix together, even if this matrix M is singular, this matrix together is not necessarily singular itself. In fact, the guarantees for when the ODE solvers will be able to solve this is essentially that a guarantee that this will not be an equation that is singular. So if you look into differential algebraic equations, right, so if you look into differential algebraic equations, which is all about, this is probably one of the most used things in actual engineering because it allows you to define differential equations that are doing things like, well, I need to have a pendulum and the length is constant, right? This is, you can, robotic systems, electric circuits, because of, you can basically write down a circuit and then just say the voltages sum to one. Pretty much most engineering systems come in the form of a differential algebraic equation, and they're very different from ODEs. And you'll see a lot of discussion if you look them up about index, and there's a lot of mathematical definitions for it. And the reason why it's so important is because normal ODE solvers cannot necessarily solve things that are a higher index than one. And so there's all these different definitions of what a high index DAE is. There's a very practical definition of it as well. And index 1 DAE is the kind of DAE where this thing right here is non-singular, so you can solve this linear system. Anything that's higher order, higher index, you have to do more work. And so what that basically means is that this Jacobian should be non-zero on the algebraic terms, because on the algebraic terms the mass matrix is zero, and that basically ensures that you have a non-singular Jacobian. So if you look into DAEs, they're a very fun topic, and really all that they're trying to tell you is that you need to make sure that the Jacobian of the nonlinear system that is solved inside of the implicit integrators is something that is non-singular, which is not necessarily the same as whether M is singular. Long story short, turning this all around, we can solve with implicit methods like implicit Euler. We can solve equations that have constraints built into them just by considering them in the mass matrix form. And instead of using I minus gamma times f prime, we just replace I with m, and there you go. Now we actually, that's the correct way to be able to do this. I mean, you also had to put m here and m here, but those are very simple matrix vector multiplications, and that handles the mass matrix directly. Why does this make sense? Why does changing I to m make sense? Well, think about it. If this was an ordinary differential equation, we'd have y1 prime equals, y2 prime equals, y3 prime equals, which would be that, right? So you always have a mass matrix. It's just usually the identity matrix. And so this I is the mass matrix of a standard ODE, which is just the identity matrix. Um, so, the implicit solvers are also really important because even if you have a small system without necessarily having stiffness, you can still have a differential algebraic equation. In fact, you can kind of understand differential algebraic equations as the infinite limit of stiff equations. So they're actually kind of always infinitely stiff. The way to understand that is you can also make this be the equation, epsilon, where so it's epsilon y3 prime equals this, where epsilon is going to 0. And so then you can also multiply the other side by 1 over epsilon. Right, so this is called the singular perturb formulation. So you can also multiply both sides by 1 over epsilon. And so when epsilon goes to 0, these two equations this is the same as the differential algebraic equation we had before, because you multiply epsilon and let it go to 0, and then this goes to 0, right? Um, but when epsilon is non-zero and just really, really small, then these terms right here are just really, really big, and so it's just like an extreme form of stiffness. So stiffness gone to the limit of infinity gives you a gives you something where you'd move this over, and then epsilon at 0 is this differential algebraic equation, which is something within a constraint. So there's a very strong connection between differential algebraic equations, handling these kinds of constraint equations, implicit ODE solvers. It's all a topic that goes together with solving stiff equations. So I thought I just might as well mention it, because it's something that, I mean, especially if you go to industry, this is something you'll see every day. So, okay, so all we have to do is we need to generate a Jacobian and solve a linear system with a Jacobian, and that's it, right? Like, if we can solve linear systems based off of Jacobians, then we can do Newton's method and we're good. There's nothing else to it. So, okay, so first of all, how do we build a Jacobian? So we went over this last time, right? So I'll defer this to the last lecture, which was all about, well, we can use finite difference method. Right, so you can use a finite difference method, which is essentially, f of, here it's a vector function, right? So f of x plus v epsilon, right? So you have a scalar and you have a vector, where this vector is the direction, right? Minus f of x divided by epsilon will give you the directional derivative in the v direction, right? If we want to calculate the Jacobian, then what you can do is you can calculate the derivative along each of the basis vectors, right? So the Jacobian matrix, f prime of x, this is a matrix where the way to calculate it is, let me change this around a little bit. The way to calculate this is to just say, this term right here. So this whole column is just going to be E1, right? Remember where E1 is the vector 1, 0, 0, 0, 0, 0. E2 equals 0, 1, 0, 0, 0, 0, dot, 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 right? So this column is calculated like this. This column is calculated like this. And dot, dot, dot. And this is E dot. Yeah. Well, no, I want to show that this is a whole column, right? So why am I showing it like this? Well, this calculates a column, right? Because when you calculate f, it gives you out a vector, right? It gives you out a whole vector. And so this is a vector. This is a vector divided by a scalar. You get a whole vector. This whole vector that comes out is the column, right? The finite difference method calculates entire columns of Jacobians at a time. And so which column you're calculating just depends on which basis factor you're perturbing by. And we saw last time, all about forward mode automatic differentiation, that instead of doing this by finite differencing, which is bad because it has numerical errors, it's reevaluating, a bunch of things all the time, right? It's not what you want to use. Instead, you want to use automatic differentiation where you put in this dual number, right? So this magical dual number, which has each of these different directions that you want with the given rules, and then what spits if you make these if you make these v's, these directional vectors, be the basis functions, you put that into your function f. What will spit out of this is each column of your Jacobian, and there you go. You've calculated a full Jacobian, right? Um, so this is the method that's used when you need to calculate full Jacobians, right? You either do this finite differencing approach or you do the forward differencing approach. You build the whole Jacobian, you do something to the Jacobian, which we'll describe in a little bit, to be able to solve this linear system, and then you update, right? So you just keep on building Jacobians, you keep on factorizing them, you keep on updating your equation until you've hit the steady state of Newton's method. So think about how expensive this is in comparison to Runge-Kutta method, right? Like even on this equation, right? So in order to build the Jacobian, you need three calls of to f because it's a vector of three things. So you need the directional derivative with respect to x, you need the directional derivative with respect to y, directional derivative with respect to z, right? So one iteration of Newton's method is doing three f calls in order to calculate this, and then it is doing another f call in order to evaluate g, right? Because remember, g has an f call inside of it, and then that's one iteration of Newton's method. So we saw last time that a fifth order explicit Runge-Kutta method is doing seven F calculations in order to do a step. And you'll see this explicitly in your homework. Your new homework, which was posted, is to implement such a method. So you're doing seven steps, but you can kind of tone it down to six if you use FSAL, right? One step of Newton's method is already using four F calls. Two steps of Newton's method is using eight. Three steps of Newton's method is essentially doubled the amount of more than doubled the computational cost of a single step of the explicit Runge-Kutta method. So doing this effectively really matters. Now, when you get to 1,000 variables, this means that if you're to try to build this Jacobian in this way, you're going to do 1,000 f calls just to build the Jacobian, and you're going to do that for every single Newton iteration. So you're talking about thousands and thousands and thousands of calls to your function f in order to just do one delta t step, instead of doing an explicit Runge-Kutta method, which uses seven of them and then does one step, but that step is smaller, right? So you need to do this efficiently in order for it to actually pay off because you are doing a lot of computations. Okay, so what's one way to make this efficient? Well, the way to make this efficient is to use sparse differentiation in matrix coloring. So this is kind of a bit of an odd topic, but it's a really kind of fun one because graph theory comes in, right? So matrix coloring actually comes from this graph theory problem of coloring graphs. And so the reason why we want to look at sparse Jacobians is because most of the Jacobians are sparse. So let's say you have an equation, right? So let's say you have one of these partial differential equation discretizations. It looks nasty, but it's one of these things like where you loop over and you say, well, du at ij is equal to the thing to the left, the thing to the right, the thing above me, the thing below. And what this means is that every single quantity only depends on five values. It depends on itself and the thing to the left, thing to the right, below, and above. So when you're writing loops out to naturally build these equations, you generally only have like a fixed number of things that are used, but there's n squared numbers of variables in this ODE. So, there's thousands. This is a small version for the documentation, but we're talking about like 1,000 squared. Like hundreds of thousands or millions of ODEs, and every single row of the Jacobian only has five non-zero terms. And so you get these sparsity patterns where you essentially just have tons and tons of zeros. And so the question is, do I need to use a million f calls to build this whole Jacobian when most of the values in there are zero? And the ways that you do this in practice is much smarter than doing this. So this is the matrix coloring method, right? So how do you do this? To understand how to efficiently build Jacobians, let's look at the following system. So let's assume that we wanted to build a Jacobian for the vector function f of x equals this vector, which is x plus 1, or x sub 1 plus x sub 3 over, oh, sorry, x sub 1 plus x sub 3, x2 times x3, and x1, right? Very simple function. Let's say we wanted to build the Jacobian, so the derivative of f with respect to all the different x's as a matrix. So let's say we wanted to do it the full way, right? So let's write this all out. So f of x plus e1 epsilon, right, for some sufficiently small epsilon is going to be x1 plus x3 plus epsilon, right? Oops, I keep on doing this same mistake here. So let me copy this over. Right, so the rule here, right, is if I'm doing a perturbation in E1, then I have 1, 0, 0. And so whenever I see a 1, I'm adding an epsilon in that direction, right? So this is plus epsilon. Dang. Oops, sorry about all this. So this is plus epsilon. This says no epsilon, x1 doesn't show up here, and this is plus epsilon, right? I'm going to write this all out because you really want to get a feel for this. You really want to see this work in practice, and then the mathematics will make it, yeah, we'll pull out the pattern. But first, you kind of want to see the pattern by eye. Let's write this out here. And so once again, now we take the system that we had before, and then we just perturb it by epsilon. So we just have x2 times x3, and then we have plus epsilon x3, right? And then we have f of x plus e3 epsilon equals, well, now we have a plus epsilon up here. And we have a plus epsilon x2, right? So there's our equations when we perturb, right? So now we want to calculate the columns of the Jacobian, right? So the first column of the Jacobian, is this quantity minus f of x, right, divided by epsilon, right? That is the first column of Jacobian. And so what we have is we have this doodad minus this doodad, and then we divide by epsilon. Like, let's see how this works out. Well, when we look at this, what we have is we have this stuff right here, this linear stuff is not touched, right? So the x plus 1 here shows up here, it also shows up here. And so when we subtract this out, what we have is we just have the, this subtracts out, this subtracts out, so we just have an epsilon left up here. And notice really clearly that, you don't have an epsilon that shows up here at all, so you get a true 0. And you have an epsilon, yeah, x1 plus epsilon minus x, so you just have epsilon here. You divide by epsilon, so what do you know? You get this vector, which is 1, 0, 1, right? Let's do the next calculation. Let's really elucidate the patterns here. The thing that I like to point out is, everyone thinks that they're special smart, but in fact, if you look at someone like Ramanujan, right? Ramanujan was well known in the way that he did a lot of mathematics was just by working out the first 2,000 digits of E by hand. And then he goes, oh yeah, there's a recurrence relationship in here, right? Or not that there's a recurrence relationship, but oh yeah, there's a better way to calculate this, right? So when you write out things by hand, you do get a real sense of how to do things better. So let's do some of that, and I think that what might be looking like magic will start to make sense here, right? Because you're already starting to be like, hey, Chris, speed up here, right? How do I speed up? Well, you'll notice that any equation where I don't have an x2, right, there is not going to be an epsilon. So if there's no x2 in this equation, then this equation is the same as this one, and so it just cancels out, right? And so you get pure cancellation if x2 doesn't show up there. And you get pure cancellation if x2 doesn't show up there. And you get not just pure cancellation, the same term shows up here and here, and so you're left with an epsilon x3. And so what you end up with here is you get this vector that is just x3, right? This is how you're calculating Jacobians through the vector calculus, right? I mean, so since I'm doing this analytically on a function that is simple enough, this has no error in it, right? The epsilon's truly canceling, but on a computer there would be a little bit of error in this, but this is the true solution it would be getting to, right? Let's calculate out the last one. All right, so f of x plus e2 or e3 epsilon, and this same pattern is going to occur, right? So we have two things that we're doing. We have that all of the equations that have an x3 in there, it's perturbing by epsilon. Anything that doesn't have x3 doesn't have an epsilon, and so we can immediately simplify it out and just put a 0 anywhere where where the equation doesn't show up. Right, and then we cancel out the term that is the same, and so this is just an x2, and this is just a epsilon, right? And then we go x2 and 1, right? Ta-da! So that's all. That's it all done by hand. So, all right. Why did we do this? Well, the reason is to start looking at different directional derivatives, right? So let's look at a different calculation here, right? So let's do the same type of method, except now on epsilon e1 plus epsilon e2, right? Minus f of x divided by epsilon, right? Well, so what we have in that case, right? So let's go back to our beginning equation. So we perturb the fraction over epsilon, and we have a minus this. Now let's write out a perturbed one, right? So we perturb both x1 and x2 by epsilon, right? So there's a plus epsilon here. And there is a plus epsilon here, which gives us this plus, epsilon x2 term again, or x3 term again, and a plus epsilon, right? We subtract off. Now let's see what this turns out to be. So we have an epsilon up here, we have an epsilon x3, and we have an epsilon, which is equal to 1 x3 1, which is equal to, well, let me kind of write something down here. 1 0 1 plus, and you go, Chris, that's trivial that those two things are equal. Why would you split it up like that? Well, let's go up a little bit above. Oh, there's that vector. Oh, there's that vector. Wait a second. This calculation, this is equal to this calculation plus this calculation, right? So we just did both calculations at the same time. Is it possible for you to know, if I gave you this vector, how to split it back up? Well, if you know the sparsity pattern, then you know the derivative of f, the derivative of the second function in f with respect to x1 is 0. So this must be a 0 here. You know that x2 doesn't show up here, so this must be a 0 here. X2 doesn't show up here, so the 0 must show up here. So if I did give you this vector of them combined, you could figure out how to split them up if you look at if you already knew the sparsity of your equation, right? So you can split this back up to be doing these two function calls. So if you can always split it up, right, this is a way to be able to do one function call instead of two of them, right? Not counting f of x, because we can calculate that once and reuse it in all of them. So it's just one factor, right? So if we have a million rows that we need to compute, you calculate f of x once, and then you do a million different perturbations, and so you have 1,000,001 f calls. I'm leaving off the 1 here, right? So this is 2 f calls instead of 1, or this, so we can do both of those at the same time. And the reason why we can do this is because the sparsity pattern works out. So let's just choose another direction then, right? Like, why don't we just start putting everything together? This is great, right? Instead of doing a million f calls, we can do one. We just use epsilon e1 plus e2 plus e3, etc. So let's be super happy, and let's start to do this, right? So um, let's do uh, let's do e2 and e3, right? All right, our super cool trick is going to work. We've solved the problem. Let's go home, right? So we perturb in the E3 direction, we got this. We don't perturb in the X1 direction, we got that. We perturb in the X2 direction and the X3 direction, and ooh-wee. Okay, so this is going to be a problem here, right? So you get epsilon 3, you get epsilon X2, you get epsilon squared, right? Because you had x2 plus epsilon times x3 plus epsilon. So we FOIL this out. Uh, so that's not good, right? Because after we cancel it here, we cancel this guy out, cancel this one out, we cancel this out, right? And so we get so we get something where we have 1, we have x3, we have x2, and we have epsilon. So that's not even defined, right? Like, yeah, this isn't just like a numerical problem. This isn't a problem of how to a. This isn't even defined, right? Because now the epsilon that you choose for the differencing will actually change the result, right? Like if you choose epsilon equal to 0, then you get something. If you choose epsilon equals 10 to the minus 5, you get a different answer analytically. Analytically, this thing gives you a different answer depending on your epsilon. That's no good, right? So why did this one, right, why did this work out, why did this example work out where we got, just the two things combined where you can split apart f, but in this example it didn't, right? And this is why you do the calculations, right? The reason why this worked is because you only have epsilons from x3 showing up here. You only have you have an epsilon from x1 showing up here, epsilon from x2 showing up here, epsilon from x1 showing up here, right? So you never have epsilons from both showing up. In this case, you have epsilons for both of them showing up, and so they confuse their perturbations, right? So this is the actual technical term here. It's perturbation confusion. You're confusing how you're perturbing in two different directions at the same time in this calculation. And so then when you're trying to then pull out what the derivative is, you have now confused your perturbations and you get a junk result. Um, so what that's telling us is that there's a key to be able to do multiple columns at the same time. And to do multiple columns at the same time, we just need to choose directional derivatives, right? We need to choose directions in our derivatives such that we do not overlap computations in any of these squares, right? Now, we didn't write this out, but let's add another equals over here, right? What is this equal to? Well, this is equal to epsilon times v, right? This is a direction. This is where, this is a directional derivative in the direction of v equals 1, 1, 0, right? Because it's e1 plus e2, it's 1, 0, 0 plus 0, 1, 0 equals 1, 1, 0, right? So this is the directional derivative in the x direction and the y direction together in equal parts, gives you both the derivative in the x direction plus the derivative in the y direction in a way that if we knew the sparsity pattern, we can split the results back out. And so this is telling us that this is a valid direction, right? So why is it a valid direction to do a multi-derivative together in? Well, because you don't have perturbations overlapping. The directional derivative of v equal to 0, 1, 1 is not a valid one because when you do the derivative in the direction of x2 and x3 simultaneously, this function right here mixes the perturbations, and therefore you cannot get any useful, you cannot interpret the result that comes out. So what we need to do then is what we can instead do is we can understand the minimum way to calculate a Jacobian, right? So this tells us that one fast way to calculate a Jacobian, right? We can't calculate the Jacobian by also perturbing in the direction of x3 at the same time. But what we can do is we can calculate a Jacobian in two directional derivatives, right? We can do it in the direction of v, and then we do it in the direction of x3. And if we have those two results, then we have the first column, the second column, and then we compute the third column directly. So that is two derivative calculations gives us three columns of the Jacobian. So there you go. That's a faster method, which is already making use of sparsity. So this is where we start to talk about the sparse Jacobian representation, right? So what this is showing you is that there is a representation of a sparse Jacobian in terms of a much thinner Jacobian, where instead what we're doing is we're representing these columns by the outputs of directional derivatives, right? So like this first column here is like mixing columns 1 and 2. It is this value. And if we know the sparsity pattern, we can take this thing and push it back over to this full sparse Jacobian, but if we're in the case where we have chosen directions such that you don't mix perturbations, right? So how do you know whether a direction is good, right? Well, what you want to do is you want to make sure that you don't mix perturbations, right? What's another way of saying you're mixing perturbations? Well, let's look at the sparsity pattern of this function, right? So let's see. So let's write down the full Jacobian. Right, so f prime of x equals, so it's 1, 0, 1, and then it's 0, x3, 0, and then it is 1, x2, 0, right? What's another way to describe the sparsity pattern? Well, anywhere where you have a 0, it's just where you don't have that thing show up, right? So the sparsity pattern, you can just look at the equation and just say x1 is not in the middle equation, so the first column has a 0 in the second row. x2 doesn't show up in the first row and the second column and the third row, and so you should have a 0 here and here. And x3 doesn't show up in this last equation, and so therefore the third column, which is all about x3, it doesn't have it has a 0 in the last equation, right? Right, because this is the derivative of the last equation with respect to x3. So you can just kind of look at your equation and just say which things show up and which things don't, and that gives you the sparsity pattern, right? It at least gives you which things are 0 and non-zero. So now how do you know when two things perturb, right? So we know that x3, so let's actually just write this down as sparsity, right? So let's say sparsity equals, and what the way that I'm representing sparsity is just like ones and zeros, right? It doesn't mean it's actually one, it just means something that's non-zero and something that's 0. And so what we want to do is we want to look at the sparsity pattern, and just from knowing that information, can we figure out how we should be doing our perturbations? Well, so remember that what we don't want is we don't want perturbations overlapping. And notice that you get an epsilon in every, like if you look up here, you get an epsilon if you have x1 showing up in the equation, right? You have an epsilon if x1 shows up in this equation. And so if you look at this tells you that, because it has, because of the sparsity pattern of the Jacobian, it has a non-zero here that tells you x1 shows up here, which means you're going to be perturbing in the direction. If you perturb in the direction of e1, then you're also perturbing 1 in the direction of the first equation and 1 in the direction of the second equation. But there's no epsilon that shows up in the second. But this tells you that there's no epsilon that shows up. If you perturb in E2, then there's no epsilon that shows up here. And there's no epsilon in the last equation, but there is an epsilon in the second equation, which means if you overlap these two, there's only one epsilon that shows up in each equation. So you can probably start to see the algorithm now on here, right? So the algorithm is that you can put together perturbations, right? You can calculate sparse matrices, multiple columns at the same time, if so you can merge two columns to happen at the same time if in any case, or if you do not have a non-zero in the same row of any of the two vectors, right? And then if you do the same process out, you can see clearly that you could even do this with three vectors at the same time if none of them if every single row only has a unique one of them that has a non-zero, right? You can do n of them. So the process is you want to choose the biggest clumps, right? So the biggest clumps are going to be the clumps that do the most columns of the Jacobian at the same time. Choose the biggest chunks that have only one value that has a non-zero in the rows at a time. So if you look at this equation, you can see, the biggest clumps that you can do is you can clump zero, you can clump 1 with 2, because this only has one perturbation, this only has one perturbation, this only has one perturbation, but you can't overlap it with the 3 because this shares perturbations and this shares perturbations. So therefore, the best you can do here is to use a directional derivative in the direction of E1 and E2 together, and the directional derivative in E3. So this is essentially an algorithm, right? Where we can say, well, let's try to figure out which things we can put together, right? And the way that you do this is now you would draw a graph, right? So you have a node for you make a node for value 1, you make a node for 2, you make a node for 3. And if there are any rows that share a 1 between, if there are any rows which are mutually non-zero between two of these columns, right? You put a edge between them. So there's going to be an edge between 1 and 3 because they both have a non-zero in the first value. So you put an edge between 1 and 3. And now you put an edge between 2 and 3 because they share a non-zero in this row, right? There's no edge between between 1 and 2 because there's no column in which they share a row. So now we have a graph, right? We have a graph where we have 1 is connected to 3 and 3 is connected to 2, and each time there's a connection that tells you that there's a shared column, right? So what we want to do is we want to pick the largest groups possible such that no two things in a group are connected by an edge. Right? So you can't choose 2 and 3 in the same group because they share an edge. So in this case, right, you have 1 connected to 3 and 3 is connected to 2. So you can choose 1 and 2 to be in the same group, and you can choose 3 to be the other group, and therefore you have two groups that will be able to do this without sharing an edge. You can see, if you think about this a bit, that this is equivalent to finding the largest groupings of compatible directions such that you don't have perturbation confusion, right? But it turns out this is actually a very classic computer science problem. This is the graph coloring problem. So if we just go look this up on Google, right, we can find, for example, hey, here's a picture that shows up for graph coloring problem. And this is what it looks like, right? So you basically just label your columns, right? So column 1, column 2, column 3 would become node 1, node 2, node 3, right? And then between the nodes, you put a line, you put an edge between them if there is any row between column I and column J such that there's a non-zero that's shared between them. There'd be no edge between these two, and there'd be an edge between node I and node J. So you do that for your whole graph, you build up this graph, and then the question is, can we find the largest set of groupings that can we find the largest set of groupings that are not touching each other, right? And now this is the same as this classic graph coloring problem, which is find the least number of colors such that no two nodes that are sharing an edge are the same color, right? So you don't have any nodes where green is touching green. You only have green connected with red and green connected with blue. Um, and so this problem of finding the graph coloring, right, tells you the smallest number of colors that are needed to have, the smallest numbers of groupings of things such that nothing in a group is connected, which if you then say, like if this is node 1, this is node 2, this is node 7, this would tell you that, you do the green perturbation, so you do the perturbation in 1, 2, and 7 all at the same time, then you do the perturbations in I, J, K, Z at the same time, right? So this means that if you drew your graph like this, and this was the optimal coloring, you could do 3 perturbations and calculate your entire Jacobian of 8 things. So the solution to the graph coloring problem is actually gives you the solution to both what is the least number of perturbations I can do to build this sparse Jacobian, and also it tells you which directions you should be using, right? Because it's all about directional derivatives, which is just something of ones and zeros, where the ones are just these values. Right? So the way that you can represent this in a computer, so if we go to something like sparse diff tools, one of these sparse differentiation packages, what you'll see is that, so this talks all about, here's one of these sparse Jacobians where you have a tridiagonal pattern. So what you'll see in here is that it has this color vector, right? And the way that you can look at this is you can say, instead of calling it, red, green, blue, you just call it color 1, 2, 3. And so, for example, in our problem, you can say that the color vector is equal to green, and so columns 1 and 2 share the same color, so they're both color 1. The next one is color 2. And so if you look at this, you can see that this is perturb in the direction of, um, you know. Let's kind of write out the code here, right? So what you do is you kind of say f of x plus you know color equal. Yeah, so in Julia code, right, you'd be like color dot equals 1 divided by, times epsilon divided by epsilon, right? This will give you columns 1 and 2 put together, and then you use the sparsity pattern to pull it apart. And then how do you get the third one? Well, you get color dot equal 2, right? Because that color dot equal 2, right? Remember when we were talking about broadcasting, right? Color dot equals 2, the Julia code. What this is it's just equal to, element wise dot equals. So it's just the same as 1 equal 2, 2, 1 equal 2, 2 equal 2, which is just going to give you 0, 1, 1, or 0, 0, 1, which is exactly E3, right? And then, you can see that when we do color dot equals 1, we get 1, 1, 1, and we get 1, 0, 0, which is E1 plus E2. Or this is that v that we define up here, right? This is that special vector that we found, that if you perturb in that direction, then you get both derivatives at the same time, right? So what you could do is you can do this matrix coloring problem. You then just read off the coloring problem and just say all the green nodes are color 1, all the red nodes are color 2, all the blue nodes are color 3. You encode it in this color vector that tells you, column 1 is associated, or column 1 is color 1, column 2 is color 2, or column 1 is color 1, column 2 is color 1, column 3 is color 2, right? And so that gives you a lot of information. That tells you both all of the directional derivatives to calculate, because you just calculate them all based off of, you loop over I and you do this. But this also tells you exactly how many F calls you have to do, right? Because you have to do color of F calls plus one, right? So the maximum number of colors plus one is the total number of F calls to do your Jacobian. So, for example, here's a case where it wants you to give you a color. You do the color vector calculation on this tridiagonal, which is essentially that you have a node 1, 2, 3, 4, 5, etc., where everything is only connected to the thing on its left and the thing on its right. And you could see that that's a sparsity pattern because I is only connected to I minus 1 and I plus 1. It turns out that you can then just do alternating by threes. So you can just do your colors are 1 2 3 1 2 3 1 2 3, and that'll work out. And so therefore you can color, so this whole Jacobian, no matter what the size of the matrix is, you can build the entire Jacobian just by calling F 4 times, right? Because you just perturb in the direction of every third value, loop over which third values you're coloring, you minus F of X, so that's the fourth one, and that gives you this this dense vector, and then you unpack it, and that gives you your sparse Jacobian. So for example, all of that these kinds of packages are looking for is they have a functionality for giving you this color vector given a sparse matrix, and then B, they have methods for doing things like, well, here you want to build a Jacobian, tell me what your color vector is and tell me your sparsity, right? Why does it need the color vector? Well, it needs the color vector to know which directions to do the derivative in. And why does it need the sparsity pattern then if it has a color vector? Well, it needs the sparsity pattern because it needs to know how to pull back apart. It needs to know how to do this operation of pulling it back apart. And the only way to do that is to know that you have a 0 here and 0, 0, right? So you do need the sparsity pattern when doing this differentiation to pull things back apart and build your full sparse matrix. It's also nice because if you want to fill the sparse matrix, you could just give it the sparse matrix and you'll know. That's the thing that you end up filling, right? Um, okay, so that's the graph coloring problem, right? So that's magic. That example that I showed, where it is just the function, f of. So I'm writing out the vector function like this, right? So just the ith version is just I minus 1 plus x of I, or minus 2xi. And the reason why I'm writing the specific one will show up when we talk about convolutional neural networks and all that, because we'll see that convolutional neural networks has these kinds of sparsities. But yeah, so if we had this, if we had a whole vector of these, then everything has this tridiagonal. You only depend on the thing to the two sides of you, and you can calculate the Jacobian for this entire function with 4 function calls independent of the number of this is independent of the number of i's there are, right? Like you can have a million by a million Jacobian, but if this is your sparsity pattern, you calculate it in 4, that's pretty good, right? An O of 1 method for something that is O of n is pretty good. So okay, that's a pretty great method. But there's only one problem with it. The problem is, if you're a computer scientist, you probably saw this coming. Um, the classic distance when coloring problem is really well studied because it is an NP-complete problem, which essentially means that there's no good way to solve it. Right? There's actually no good way to solve the coloring problem if you have a really big coloring problem. Um, it's an NP-complete problem, which means it has the property that if you give me a coloring, I can instantly tell you, um, like, yes, this coloring works, or no, it doesn't work. But it's really hard for me to be able to say this coloring is optimal, right? It actually takes, currently given what we know, and this is about P equals NP, kind of, $3 million prize. Currently, from what we know, the best way to do this calculation takes exponential calculation time in n, right? It's more than polynomial. Um, the P equals NP problem, if you can prove that you can do graph coloring in polynomial time, so like, if the amount of work it takes to solve this problem is the number of nodes cubed, right? If you can prove that was true, you get $3 million. That's how much people care about the solution. But right now, that is actually one of the biggest open problems in mathematics. So if we want to do and it's not even clear that it's possible to do this polynomially. So it basically takes an exponential amount of time for larger and larger graphs to be able to solve the matrix coloring problem. So there is your trade-off, right? Like, you can take an arbitrary million by million sparse Jacobian and find out that you only need to calculate it in 4 directions by using this very specific coloring. But actually finding that coloring can take exponential amount of time. So what do? Well, you don't solve it exactly, right? So the color of the graph, or its chromatic number, is the minimum number of colors. We can relax that a bit. And instead of finding the minimum number of colors, we can just ask for a good number of colors. And there's some easy greedy algorithms, right? So this one actually can be solved by the greedy algorithm. So what you do is you move your mouse around and you pick a node at random, right? We pick this node at random and we give it a color. And now what we do is anything that is anything that's connected to it. Let me try to so make anything that's connected to it, make it the lowest color that it could be, right? So here this is color 1. This is connected to color 1, so it can't be color 1, so let's make it color 2. This one is connected to color 1, so it can't be color 1. But it's not connected to the one that we already made color 2, so let's make it a 2. And and this one is also yeah, so okay, so this one can be a 2, and then this one is connected to color 1, so we can make this color 2 too, right? So this algorithm that just came, this greedy algorithm would have made this one red, this one red, this one red. Now you do that again. So now we go to this one, right? Now I go to that node of the graph, and I say, well, what is this node? This one can either be blue or green, so I'm just going to make it a 1 because that's the lowest I can make it. This one could be this one is not connected to a 1, so I'm going to make it a 1, right? So you just keep on going to all these, looping through the ones that you've already seen, and you just make it the lowest color that it could possibly be, and you just loop through the graph. That is an O of n algorithm because you only have to look at each thing once. You go to that node, you decide what is possible with it given the current things you've already chosen, and you choose that color, you move on, right? It's not guaranteed to get, it's not even close to guaranteed to give you the minimum. It definitely doesn't give you the minimum. It's easy to come up with counter examples, but it can be a pretty good algorithm. And so generally when people do matrix coloring, you have many different algorithms, many different greedy algorithms for coming up with different colorings. And some things are better algorithms, some things are worse, and most of them are some form of approximation because the real problem is too hard to solve. But that is essentially the matrix coloring method for sparse differentiation. You take a graph with the sparsity pattern, you then come up with the, you split it up by its sparsity pattern. You find the Jacobian columns that can be computed at the same time, right? But you by putting together columns, by looking at the connection matrix, and just choosing something that satisfies the coloring problem. Right. And that is what you do to be able to calculate these really large Jacobians efficiently. And now, what about forward mode AD, right? Because I just did this whole derivation in terms of forward differentiation, but last lecture I told you that you should never do that, right? You should never do forward differentiation. Well, for forward mode AD, it's essentially the same thing, right? Where remember that when we do forward mode AD, we give it these directional derivatives, we give it these directional vectors, right? And what we want is we want to make sure that the algorithm works in such a way that E1 and E2 never show up in the same equation because they need to be 0, right? And so the same exact thing applies, where if we build a dual number where these directional derivative vectors v, so if vi is the vector of colors equal to I, then you put that dual number defined by the directional derivatives being the color vector directions. The value that comes out, the dual number that comes out that matrix from the dual numbers is actually the sparse compressed representation of all of your different derivatives, and you just pull it apart using the sparsity pattern. So it's almost the same exact process as what I just showed here, except the whole process. This is why we went over forward mode AD as directional derivatives, right? Because then to do the sparse matrix differentiation, all that we do is we change our inputs from being e1, e2, etc., to being the color vector directions, and then the output is the sparse of the compressed form of this of the Jacobian, and then we decompress it out to the full sparse version. So this same process, the same exact color vector and everything, that's all used, and then you use forward mode AD instead of you use forward mode AD with directional derivatives instead of finite differencing with directional derivatives, and that's how you do forward mode AD for large sparse Jacobians. So that's our best method so far. I do want to make a note about reverse mode AD. So we haven't got into reverse mode AD yet, but I do want to make a note about something. The way that reverse mode AD works, we'll see, is that it's all about calculating entire rows of a Jacobian at the same time, right? So forward mode AD and finite differencing, so numerical differentiation, calculates one column at the same time. Complex step differentiation calculates columns at the same time. Reverse mode AD is an entirely different process where it calculates rows at the same time. And so you can do this exact same thing to be able to do sparse reverse mode AD, right? How would you do it? You would create a graph where you have a node be each row. You would put you would put a link between them if the two rows, if the two rows have a shared non-zero and some column between them, right? So you're basically doing the matrix coloring of the transpose of the sparsity pattern. Um, and then you would do that. Then you use colored reverse mode differentiation, and that would give you the compressed version in terms of squish in terms of columns, and you expand out the columns because you don't have perturbation confusion. So we'll get into reverse mode AD. I'm not going to mention this again on there, but really the idea is the same idea for how do you do compression, build the compressed Jacobian, and then decompress it. It works on reverse mode AD just by using the rows instead of the columns in the way that we do the compression. So that's how you build really big Jacobians really fast. Okay, so let's go back up to Newton's method because that was kind of a long explanation. Let's see where we're at. So we use implicit Euler. We move everything to one side. We get g of x equals 0, right? Now we figure out that we have to do Newton's method, but Newton's method we don't actually find the inverse of the matrix. What we do is we find the Jacobian, we solve the linear system, we do an update, then we find the Jacobian, solve the linear system, do an update, and we repeat this process, right? Um, okay, we know how to calculate the Jacobian. How do you solve this linear system then? Okay, so now we have the Jacobian. All we have to do is we need to solve, Jacobian vector equals vector, right? Where we know B, we know J, what we want to find is A. So I'm not going to go into the details of this too much because this is if you want to know all about this process, this is the core of numerical linear algebra. So when people work on numerical linear algebra, they're talking about matrix multiplication and they're talking about factorizations and eigenvalue problems. But these factorizations are very in depth in with the way that they work. So I'm not going to give the full information on factorizations, but essentially, what you do here is Gaussian elimination. And when you do Gaussian elimination, you do something like, let's. So let me get to that point, right? So what we want to do is we want to find J equals L times U, where this is essentially two matrices, right? So we have one matrix and we have one matrix. Right, and we basically want values like I'm just putting x's for things that are non-zero. We want one matrix, which is lower triangular, and we want another matrix, which is upper triangular. And we want to find these two matrices such that when you multiply them out, you get the original matrix. Now the reason is because this is if we find this, we've essentially solved the problem, right? And why have we solved the problem? Well, let's look at J A equals B. Then we can write this down as LUA equals B. And now we can do A equals you know, L inverse or U inverse L inverse A. You don't want to actually do this process of calculating inverses, but what I can tell you is solving the linear systems based off of these things is trivial. So let's go back one step then. All right, so LU equals A. Let's solve let's solve the linear system. Let's solve for what U times A should be, right? Let's do that first. Well, we have this linear system, which is essentially of the form, right? Yeah, so we basically have something that's like this times C. Oops, that's not what I wanted. We have a matrix which is like this times x1, x2, x3 equals to b1, b2, b3, right? Oh, so let me make this a so that way I'm not changing my notation. Oh, well, let's make it x because x equals ua, right? So for x equals ua. So okay, so if you multiply this out, the system that you get is let's call this like coefficient 1, coefficient 2, coefficient 3, coefficient 4, coefficient 5, coefficient 6, right? So if you multiply this out, what you get is coefficient 1, x1, coefficient 1 or coefficient 2, x1 plus coefficient 3, x2, coefficient 4, x1 plus coefficient 5, x2 plus coefficient 6, x3 equals b1, b2, b3. And now this is something that you probably know how to solve from high school, right? Like what is x1? Well, x1 equals b1 divided by, yeah, so let's just write this out. So x1 equals b1 divided by c1. So then x2 equals, b2 minus c2 x1, because we know x1, we can do this, right? And then we divide this by c3. Right, and you keep on doing this process. So x3 equals, and if you've seen this before, you know that this is called the back substitution method, where if you have a lower triangular or upper triangular matrix, you can do this process of you solve for the first thing, then you get the second one, then you get the third one. All right, I'm gonna let me just write it out because I'm already here. X2 divided by CX3, right? So you calculate the first one to get the second one to get the third one. And then if it's a upper triangular matrix, then you calculate you'll see that you get the exact opposite pattern. And so then you calculate the last one to then get the first, the second one to get the first one, right? So this is back substitution. So it's very easy if you ever had a lower triangular or an upper triangular to solve the linear system without inverting the matrix, right? Because this doesn't involve an inverse of the matrix. You're just inverting term here, and then you're solving next term, solving next term. So great, we got a way to do this. So if you can find out L and U, which is the part that we're going to leave off because that's a whole thing. But it turns out that calculating L and U is equivalent to doing Gaussian elimination, because what you essentially do is you say, well, remember Gaussian elimination. You say, oh, subtract row 1 from row 2, right? You can write out subtracting row 1 plus row 2 as, my original matrix J is equal to E1, where E1 is the elementary operation of subtract row 1 from row 2, which is the same thing as saying, it's this vector of, 1 subtract from 1, 0, right? So you can write out your elementary vectors, and then you can represent, so this U matrix is what happens when you multiply all these elementary vectors together, and this lower triangular matrix over here is the result of Gaussian elimination. So this is Gaussian elimination under the hood to be able to do this. Um, and that's how you get the L and U. And once you have the L and U, you can just do this back substitution, be able to calculate what A is without ever building the inverse. So, okay. There's a generalization of this to sparse matrices to be able to do a sparse LU, and where it can have a given amount of sparsity pattern. It does have some fill-in, so it's not as sparse as J, but it's not dense. It's not dense triangular. It is much sparser than that. So that is a way to be able to then make this work on really large sparse matrices for solving these really large stiff equations. So there's always caveats with all of this, right? Um, so one caveat is that the system for doing back substitution, right? This is going to be an O of n squared method because you have one calculation you have to do here, you have two calculations here, you have three calculations here, and so you have I many calculations n times, and so you have that classic n times n plus one total number of operations. By looking at the triangle, Pascal triangle, or not the Pascal triangle, but it's looking at the triangle. You get O of n squared operations you have to do this back substitution. But the computation of LU itself is Gaussian elimination, and Gaussian elimination is an O of n squared algorithm, or O of n cubed algorithm. So if you have a very, very big Jacobian, this is an expensive calculation to do. So it is a very expensive calculation to build a Jacobian. Then it's but it's can be an even more expensive calculation to factorize it. So you can make the building of a really large Jacobian cheap if it's sparse by doing sparse coloring and sparse differentiation. But even sparse LU computations are pretty expensive. So this generally is the most costly part of stiff ODE solvers, just computing LU. And this is a problem where it's not specialized to differential equations at all, right? You just have a matrix of numbers, and you want to turn that matrix of numbers into LU to be able to solve a linear system. This is something where things made not for differential equations are utilized under the hood inside of a differential equation solver for this step, and it's very heavily optimized, et cetera, et cetera. You have different versions for different types of sparsity patterns. And that's a whole class on its own. You can take a whole course which is just all about how do you do that factorization process. But let's go look at our Newton's method again, right? So this is what you're doing, right? You are doing this operation, and you're doing it by solving this linear system. You update. You solve this linear system. You update. But it'd be really nice, right? Since solving this linear system is really just calculating the LU factorization. If you've done it and you can keep it, then once you've calculated LU factorization, you just do this back substitution with different coefficients in there, and you can keep on redoing it. And that's only O of n squared, right? Compared to O of n cubed, that is tiny. So if you could keep your factorized Jacobian, that'd be great. You can't keep your factorized Jacobian, though, because your Jacobian changes every single time, because Newton's method needs to evaluate the derivative at the new x each time. So in your homework, we did look at this, though, right? There's a method that is pretty stable, and it's the quasi-Newton method. And so the quasi-Newton method is where you just use the Jacobian evaluated at your first point, and then you keep on using that same Jacobian over and over, right? If you do that, then you just have to factorize, you only have to factorize the Jacobian once. You do a bunch of back substitutions. You still have to do a bunch of back substitutions, but it's okay because those are all O of n squared. So you're doing a ton of O of n squared operations and only doing one O of n cubed operation. Will this be better or worse? Well, quasi-Newton is a little bit less stable than Newton's method, and so what that ends up meaning is that you can end up taking larger time steps and have worse guesses for the x0 if you use Newton's method. But in general, it is such a huge computational time decrease that pretty much any good stiff OD solver is using a quasi-Newton method in there. So okay, this brings us to, we started by saying we're going to use the Newton's method, but actually what we're going to do is we're going to use a quasi-Newton method. The way we calculate this Jacobian is not the standard way. It's actually going to be, forward mode automatic differentiation with partials, where the directions of the partials are given by this, by solving a NP complete graph coloring problem, and then after we get that Jacobian, then we use a LU factorization or a sparse LU factorization to be able to do this computation. Parallel. This is a place where you would parallelize the operation. Big distributed factorization problem. So there you go. So there is already a very complicated form of the stiff ODE solving where we've really brought down the size, the computational time to build the Jacobian and to solve the linear system, and the memory cost of representing the inverse when trying to do the Newton's method. Right? And so this is like the key to, if you were to do this solving on one computer, that's how you do it. So what happens if we want to go beyond that, right? So there is another method in here, which if you can do if the sparse factorization works, right? If the sparse matrix fits into memory, then the sparse factorization is generally better. That's not always true, but it's generally better. Otherwise, what do you do if you cannot even build that sparse matrix? It turns out that you can do Newton's method without ever building the Jacobian. And this is called Jacobian-free Newton-Krylov. So the first thing is, can we, the first thing that I want to figure out is, well, we want to solve this equation JA equals B, right? Which is really just, we want to see if we can calculate a Jacobian times a vector, whether that equals B. Can you think of a way to calculate a Jacobian times a vector without ever calculating the Jacobian? Correct. The answer is either finite differencing or forward mode AD. We didn't go over this last time, how to do this with finite differencing, but the Jacobian at x times a vector, this is approximately equal to f of x plus v epsilon minus f of x divided by epsilon, because Jacobian vector products, that's just a representation, another representation of the directional derivative, right? That's the derivation that we went through last time. So you can do finite differencing like this, and so with two function calls, with two calls to f, you can get Jacobian vector products. Remember, with forward mode AD, you just define a dual number which has one partial vector, and that partial is just the direction v, and that is the same thing as calculating the Jacobian times the vector v. So calculating Jacobian vector products with forward mode AD is very simple. We're going to get to reverse mode AD in this next lecture. So let me just kind of make a comment here that reverse mode AD is actually very similar, but what it naturally calculates is vector transpose times Jacobian, right? Or another way of writing this is Jacobian Jacobian transpose times vector transpose, right? So what it, if you need to do calculations against the transpose of the Jacobian, or a left multiplication by a transpose of a vector, reverse mode AD is a similar trick, or is a trick that does a similar thing, but instead it does this operation instead of Jacobian vector products. We'll see in the coming lecture that this is actually equivalent to that idea that I said before, that reverse mode AD is all about calculating rows of Jacobians. But we'll skip on that for now because we actually just need Jacobian vector products for this part, right? So okay, we can calculate Jacobian times vector products really easily, but that doesn't help us if we actually need the matrix in order to do LU factorizations. So that brings us to Krylov subspace methods for solving linear systems. So now let's kind of isolate this problem here, right? So we have J times W equals V, and we want methods for calculating this without inverting the J, right? We don't want to do this, and we don't want to do a factorization because in this case we're saying we don't know what J is, but we can the only thing we have available to us is to calculate J times X, right? If you give me a vector X, I can calculate J times X, but I don't know what J is itself, right? So can we solve a linear system with only that information, with only the information about how the Jacobian multiplies against other vectors? Um, so to do this, right? Well, let's move things to one side. To do this, what we want to do is we want to find the vector that does this, or let me yeah, so I kind of messed up my notation here, so let me make it match, right? So let's say we want to calculate this. Well, to solve this problem, what we really want to do is we want to find JW equals 0. So we want to find W such that we find the 0 of this equation. So what do? Well, we're using the same trick over and over, right? So instead of actually solving the equation directly, we can define a discrete dynamical system, right? So we define a discrete dynamical system with some, W sub I, where what we want this to do is we want W sub I to converge, right arrow, to W star, where JW star equals B. Right. So we want to define a dynamical system that will have this property that if we do this, we do some kind of iteration in a loop, we'll go to some W star such that it's the solution to this equation. So how do we do that? Well, the way that we're going to do this is, let's say we can split J equals into A and B. So let's say, J equals A minus B. We'll come back in a second how we define A and B. So if we do that, then let's plug this into let's plug this into this. Well, let's write this down here, right? So right. So let's think about this another way, right? So if you have things converging, right? If things converge, then yk plus 1 minus or wk plus 1 minus wk should be going to 0 as k goes to infinity, right? So let's do this right here. Well, what this means is, what this means is that, for k very large, then we should have that wk plus 1 is approximately wk, right? So let's split this up. So what we want to solve is we want to solve jwi equals 0. But approximately, it should happen that a wk plus 1 minus b wk minus b equals 0. Or we can move things back over and say a wk plus 1 equals bwk minus b, right? So this is almost an iterative process where if we pick a starting point, and then we pick a starting point, and then we loop through this, we get wk plus 1, wk plus 1. We keep doing this until we converge to something, and that what we converge to will be the solution of the linear system. Okay. Well, yeah, why is the convergence going to give you the solution? Well, because once you get convergence, then that means this is going to 0, which means that you cancel this out, and et cetera, right? So you can write that down. Now you can't do this loop yet because you have A here, right? So you do need to be able to invert A. So that means that our iterations are going to be wk plus 1 equals A inverse times this. Right? Now this is an iterative method. but it requires that you calculate the inverse of a matrix, which is exactly what we didn't want to do before, right? So why is this different? Well, we just have to choose A and B such that they sum up to J, and we only need to take the inverse of the A portion. So we can choose A to be something that is easy to take the inverse of, right? So I wrote in the lecture notes here a few examples. Like Richardson's method is you just take A to be equal to the identity matrix times W, or times omega, right? Why would you do that? Well, because omega equals what's the inverse of A there? Well, it's just 1 divided by omega on the identity matrix. So it's easy to calculate the inverse here, and this gives you one dynamical system, right? Um, there's a nice general way that which a lot of methods come from. So if you let J equal to lower plus diagonal plus upper, which is essentially, if I write it down in this 3 by 3 form, what you can do is you can write this as lower plus diagonal plus upper, right? Where you have here it's going to be the strict lower diagonal, this or strict and strict. So this is what I mean by du and L. So if you were to have split it up like this, so if you knew the matrix and you split it up like this, then Jacobi's method would be where you make A equal to just the diagonal. How do you invert a diagonal matrix? Well, it's just the inverse of each of these components, right? That's easy. The dampened diagonal is where you multiply the diagonal times some constant, right? There's a method called Gauss-Seidel where what you do is you take the diagonal and you subtract off the lower side. This gives you one of those lower diagonal matrices that we saw in the LU portion, right? Which means that solving this inverse problem is just solving this problem right here. Inverting A is just doing back substitution like we defined above. And so that's another combination where it is easy to invert, right? So you can also dampen the D here. That's called successive over relaxation, or you can make it a symmetric success. So there's all these different choices here, but essentially what you want to do is you want to choose a portion of J that is easy to take the inverse of. The biggest portion of J that is easy to take the inverse of, and then only use the inverse of that in this iterative procedure where you're capturing the other parts of the matrix in B. And if you run this iteration long enough, it will converge to give you the solution to your original problem. Right. So the whole game is really, how do I choose the biggest thing to take an inverse of, but not make that inverse problem be very hard, right? Like the factorization problem itself, you can think of it as one of these, where you basically just choose A to be equal to J, and you let B equal to 0 matrix, and you can then look at this and see that you will converge in one iteration, right? So factorization is essentially one of these methods, but these are methods where you can kind of use an approximate factorization over and over and over, and then that factorization from the approximate will converge. So that's one type of iterative method. This isn't an iterative method that you can do with matrix-free methods, but it's just this is like a much more clear style of iterative method that we wrote down the dynamical system. We can see its convergence. You do have to analyze things like what's its stability and all that, and that's the core of a numerical linear algebra course. But okay, so that's one way to be able to do an iterative method to solve a linear system. What's another method to do that? These are the Krylov subspace methods. And essentially what you can do is you can so if you were to build this Krylov subspace, what the Krylov subspace is the vector v, the vector j times v, the vector j squared times v, etc. There are nice properties of these Krylov subspaces, right? So it is known that there is a finite maximum dimension to the Krylov subspace. The reason is because each of these are you can show that each of these vectors that come from the Krylov subspace are going to be um, they're not orthogonal, they're linearly independent of each other, so they're all capturing a new dimension. And so if you do this for at least the number of columns in the matrix, you will have captured something with the same dimensionality of the matrix. Going back to your linear algebra. Um, so there is a method essentially in here which says, given a Krylov subspace, which is some some number of these Krylov vectors, multiplying up to some j to the kv, it gives you the approximation to um, the linear system solution. So just by using j to the kv, so using v, j to the kv, j to the or yeah, so we remember that we want to solve JW equals V. We want to solve for W, right? It turns out by using the vectors V, JV, J squared V, J cubed V, right? Dot 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 up to some JKV. It turns out that if we have these vectors, there is a method called GMRes. There's a method called GMRes, which gives you the JW minus V. It gives so it gives the vector V such that the norm of JW minus, or let's say WK here, such that the norm of this is minimized. Minimized. Yeah. So okay, so there's two facts in here, right? So you can prove that this converges because if you had your entire Jacobian, then the W that so I'm not going to go into this method for how it does compute the vector WK that is the vector that minimizes this distance, but it does, and it does this fairly cheaply, right? So if you have, all of these vectors, then you can find the WK that minimizes this difference, and you can know that you can know that this converges, right? So why does this converge? Well, um, because each of these Krylov subspace vectors are orthogonal. Um, Right. Well, okay. They're not orthogonal, but they all span a different direction, and so once you prove that they're going to be linearly independent, then you know that after you match the size of your Jacobian, after k is equal to the number of columns in your Jacobian, then you have a set of vectors which spans the full space, and therefore what this is basically saying, find WK in the full space such that you minimize this, and so you can guarantee that um, in that many vectors, from that many vectors, you can get the true solution out of here, right? But instead, you can say, I want to just find the approximate solution to the linear system up to some tolerance. You just need to figure out how many Krylov subspace vectors to get to be able to calculate it that. Right? So how do you calculate these Krylov subspace vectors? Well, remember that j squared v equals jv. So a Jacobian vector product gives you the first one. A Jacobian vector product where the vector is jv gives you the second Krylov subspace vector. Jacobian vector product of the where the vector is j squared v, it gives you the j cubed v vector, right? So you just keep on using you iteratively do this Jacobian vector product trick to build up all of these vectors without building the Jacobian. And then each time that you build a new vector, right? So each time you get a new vector, that's one f call. You do the f call, and then you do the GMRS method to check how close you are to having something that's a solution. If it's not close enough to tolerance, then you get the next vector. Right, you just use this one. You just vector Jacobian product where the vector is this, and then you have the j to the k plus 1th power one, right? You see, is that good enough? Is that good enough? Is that good enough? You're guaranteed to have something that solves the linear system to your tolerance if you do that for the number of columns iterations. But you then just stop it earlier where you want. Um, so that gives you a way to be able to solve this linear system with only using Jacobian vector products. And if you can solve this linear system with only Jacobian vector products, then what is Newton's method again? Well, you can go back to doing straight Newton's method, where you say, I solve this by using Jacobian vector products and Krylov's subspace method to get the vector A out, and then I get the xk plus 1 by doing this, and then I move back, move back, move back, and you loop through this, right? It's just doing a ton of f calculations, um, but that's okay. So that's the intermediate conclusion, right? There's two methods that could be faster. One is to really easily and quickly build the sparse Jacobian and then factorize the sparse Jacobian if that fits into memory. Or if the Jacobian doesn't fit into memory, we can use these Krylov subspace methods. Which one is better or worse? Well, it depends on the rate of convergence of this, right? Remember that when we have a big sparse Jacobian, you only need to use color vector many, the number of colors in that graph tells you how many the number of color vectors in that graph tells you how many function calculations it will take to be able to build that large sparse Jacobian. The number of function evaluations that it takes to be able to build the Krylov subspace, the k Krylov subspace vectors is k. And so if this converges really quickly, then that can be faster than doing the sparse differentiation. If it converges very slowly, then it's also then it's not good enough, right? Then it can be faster to do the sparse factorization. At the same time, remember, going back a little bit, there's a lot in this lecture, so you might want to go back through it again. Um, so going back a little bit, with sparse factorization, we can also do the factorization once, use a quasi-Newton method, and reuse it for all Newton iterations. So we need to find new Krylov subspaces every single time when we go through the Krylov subspace solver. So that's another thing to keep in mind. Like, one can use quasi-Newton effectively, the other cannot use quasi-Newton as effectively. It needs to use full Newton, and those have different convergence properties. So knowing which one will perform better is actually just kind of guess and check. Usually, one thing to know about, though, that is very important is preconditioning, right? So the key here really is that if this converges, if this process converges very fast, then it'll be faster than sparse differentiation. But it turns out that that your convergence is slower when your matrix has a higher condition number. Your condition number of your matrix is defined by the largest eigenvalue divided by the smallest eigenvalue. Which, remember, when we're talking about stiffness, is a very large difference because that's time scale separation. So by definition, you have an ill-conditioned matrix whenever you're doing this, and so standard GMRes will kind of have bad convergence without doing something to correct that. And that way to correct it is called preconditioning, right? And here's how preconditioning works. So you have the matrix J, and what we want to do is we want to find something equivalent to J, which is PL A PR, right? So instead of solving Jx equals V, instead solve, right? Well, let's plug in the thing there, right? So we have PL A PR x equals V. So instead of solving Jx equals V, we plug this in. And what we can do is we can write this as A PRx equals PL inverse V. Right, so this is what we call the left preconditioner, and this is what we call the right preconditioner. So the right preconditioner is just like it's a projection of our x. The left preconditioner is really significant here, though. Basically, what it says is that if you can pull apart a part of the Jacobian, which is easy to invert, then you can use that known inverse to be able to make the linear system that you're trying to solve easier, right? Because now the only you project this onto x. Now you just have to solve the linear system. A times this vector equals this vector, right? And so you can try to choose the left preconditioner and the right preconditioner such that it has eigenvalues which are closer together. You know, the largest eigenvalue and its smallest eigenvalue are closer together, and PL is easy to invert. So you can do these same tricks like we did above, right? So you can try to pull out a lower, well, you don't want to pull out a lower triangular region because that's equivalent to doing LU factorization, right? Um, but you can try to like pull out the diagonal, right? So if you have a good guess for what the eigenvectors are, you can make PL be equal to the diagonal, right? And then you can you can invert this side by the diagonal, and hopefully what that will mean is that you're changing the smallest values over here. You're changing them to be much larger. You're changing the sizes of everything to kind of be the inverse of your eigenvalues. So then you're kind of squeezing the solve together, and so A should be easier to solve. Um, there's all these different ideas for that. So if you ever heard of multi-grid methods are essentially a way of doing this. And this is called preconditioning. So you precondition this, you make the Krylov subspace easier to solve by decomposing it and always, knowing the inverse of PL and then using the inverse of PL to make the Krylov subspace problem for A easier. And once you've solved this, you just multiply it back out and you get back out the solution to the original iterative system. Um, okay, so that is how when you have these very large Krylov subspace methods. So, for example, the Klima climate model, which is being built by Caltech and MIT, right? What we're working on internally, like what I work on with that is essentially how do you do these really large sparse, systems where you can never fit this Jacobian for the full climate model anywhere. It's already a big distributed computation. So all of their computations are Krylov subspace methods, if they want to do an iterative time stepping method. And so, then it's all about what are good preconditioners for solving the sparse systems that come out of climate models. Um, so that's Krylov subspace methods. But the other thing is, so let's go back to Krylov subspace methods. Optimizing them is all about doing Jacobian vector for calculations really fast, which is the 80 trick that I mentioned, and it's all about picking good preconditioners. So what about Jacobian? So what about quasi-Newton methods, right? Let's write that down again. So quasi-Newton method is xn plus 1 equals xn minus, you know, uh, this Jacobian inverse at x 0 um, g of xn, right? So we already did one approximation, right? So technically, in Newton's method, you need to invert a new Jacobian each time. So technically, in Newton's method, you have to factorize the new Jacobian every time. But instead here, we can say, well, we can make this faster without losing too many good properties by only using a single Jacobian, and then we just factorize it once, and we're good, right? If we're doing the factorization method, well, if we factorized at one time step before, it turns out that, if this is from un minus 1, that could also be a good enough approximation. Yep. You showed in your homework that, you can, perturbations of this should converge. Um, so I mean, if un plus 1 isn't too far away, then that could be a good one. Un plus minus 2 is not too far away, that could be a good one. And so what this really is really telling you is that if you use the sparse the sparse factorization form, you can factorize a Jacobian once, use it in all of your Newton iterations to get your un plus 1, and after you do a time step in the ODE solver, then in your next Newton solve, right, you can reuse that same factorized matrix, unless if you're diverging, right? Like if this is too bad, it'll cause divergence in the Newton's method, because it can only be perturbed so far away. But if you start to see that your Newton's method is diverging, then you calculate a new Jacobian and you factorize a new Jacobian. So you can keep the same Jacobian for many steps. And this is really one of those tricks that's utilized in these very fast ODE solvers. So let's kind of go back to this again, right? Because this is kind of going many stacks deep here, right? So every step of the ODE solver is, right, un plus 1 equals u sub n plus delta t So every step of the ODE solver is un plus 1 equals u sub n plus delta t times f of u sub n plus 1, right? Which is solved by, so we move everything to one side. Right, so now I'm just kind of doing a recap here. We move everything to one side, which is the same thing as saying g of un plus 1 equals 0, which is then solved uh, using Newton's method. So xn plus 1 equals xn minus, let me call it g prime here, g prime of x and g of x n, right? Where xn converges to x star, where g of x star equals 0, which means x star is what we which means that what we want to use is that un plus 1, right? The next step of our stepping forward on our ODE solver is that solution is the thing that Newton's method converges to. Right, so that's how these two things come together, right? So what we were really trying to solve is we're trying to just do one step of an ODE solve, and in order to do one step of this ODE, right? So an ODE solve is an iterative method, right? In order to do an iteration of the ODE solve, we turn it into Newton's problem, and so we have to iterate a Newton method in order to get that one step, right? But in order to use Newton's method, we have to solve, g prime w equals v, which we need to solve that every iteration. And how do we solve that? Well, we can use a factorization method. Or we do an iterative method, right? So we solve an iterative method here to get one step of Newton's method, and then we iterate Newton's method, iterating this thing underneath it to get the one step of the ODE solver, and then we move to the next iteration of the ODE solver. So we're going 3 steps deep in the iterations here. So that's why you can see that this is a much more complicated method. And at the bottom here, you keep on having to, if this is a Newton-Krylov method, every single time that you do an iteration here, you're building a new vector of your Krylov subspace. So that's another vector Jacobian product, and so that's another function call, right? So this is function calls upon function calls upon function calls just to be able to do this process. So your hope is, that your delta t from this is 1,000, 10,000 times larger than with the Runge-Kutta method. That's like a global view of the method that I mean I've spent this whole time explaining, and it has been a wildly long lecture, split up into different parts. But this is the core idea at the end of it, right? That we're nesting these iterations all together, and the result of it is a method that tells you how to step forward on this, right? Where there's sparse factorization and matrix coloring and graph coloring problems. All this is thrown into this one step, and this is why I say a stiff ODE solver is 2, 3, 4 orders of magnitude more complicated than a non-stiff one. So yeah, what are some things to kind of to pick out on this? Well, some interesting details is that this delta t here does show up in this Jacobian, and so it turns out that using smaller delta t's, there's two things that happen here, right? That kind of keep aware of, right? So if delta t is smaller, then the coefficients of the Jacobian are smaller. And so this is actually the same, it's very similar to the Newton relaxation, which you showed in the homework, right? So in the homework, you showed that using a relaxation factor on the Newton's method makes it more stable, makes it easier to converge, right? And so decreasing delta t means that you have a better chance for this Newton method to converge. The other thing is that if your best guess for the x0 is closer to xn plus 1, um, is closer to x star, then you have better stability, right? That's another thing you're looking at in the homework. Well, if delta t is very small, then un plus 1 is very close to un. So as you decrease delta t, there are multiple different reasons why this Newton method becomes more stable. So there is a largest so now like inside of the last lecture we showed that there is no limit to delta t that is stable for this solving this equation, right? But for solving this equation, the Newton's method, right, there is a maximal delta t for which the Newton method will not diverge in. So this becomes a whole balance game, right? You want to choose the largest delta t such that you get the error that you want out of the method, right? Because remember, you're always balancing error. So you want the largest delta t that gives you something that is within the error tolerance you want of your ODE solver, but you don't need to worry about stability here, but sometimes you do. So you also want your delta t to be chosen such that you have stability, but also you want your delta t chosen such that you have stability in your Newton method, where not only in your Newton method here, but also turns out that your Krylov subspace has is less ill conditioned if you use a smaller delta t. So you choosing a smaller delta t can also decrease the time it takes to solve the linear system. So you're trying to choose the maximum delta t that lets you solve the system fast, lets the system be stable, and lets this thing have low enough error. And so this is generally something where fixed time step methods just do not work well, right? The reason why fixed time step methods generally do not work out well is mainly because of this step. Because if you chose a delta t and your Newton iteration fails, you're out of luck. So what you really do here is your stiff ODE solver will try a delta t. It'll try to solve the Newton's method. If Newton's method diverges, then it shrinks delta t and then goes forward and then tries to choose a new delta t. So adaptive time stepping is really key to doing any stiff ODE solving. And so how do you do stiff ODE solving? Well, what you do is you solve an ODE with two methods simultaneously, and the difference between those two methods is going to be an approximation to the error. And once you have an approximation to the error, you can say, well, I want to so let's say the error is 2 times as much as you want. Well, then you can take if you take half of delta t, right? So remember that your error is approximately O of delta t here, right? So if your error is 2 times as much as you want, then if you take half of the delta t that you had before, your error should be about correct, right? So this is called the proportional control method so you use two different methods, which we can describe in more detail. You use two different methods, you subtract their results together to get an error approximation, and then you use a constant with something proportional to that error constant or to that error calculation to tell you q, where your next delta t should be based off of q, q times delta t. It's proportional. So the change in delta t is proportional to the error that you had. And so if you use this kind of method, then what you do is after a successful step, this tells you what your delta t should change to. Or if you have Newton divergence or it's something, this tells you how you should change delta t. And then you keep on doing these iterations for the linear system to be able to get the iterations for the Newton's method, to get the iterations for the ODE solver. You rinse and repeat, rinse and repeat, rinse and repeat until you've solved the whole ODE. And that is stiff ODE solving in full with all the sparsity, with all the automatic differentiation and everything put in there. And so there's the summary at the very bottom, that at the lowest level, you're solving a linear system either through Jacobian free Newton Krylov using the forward mode automatic differentiation trick, or you build the full Jacobian by using these color vectors and you do a sparse factorization, right? Or at the next, and then, so if you can solve this linear system, then you've graduated to the next level, which is you do a Newton's method, which is just iteratively doing that linear system solving. And if you can do that, then Well, then you can, then the steps of the ODE solver is just doing iterations of that Newton method. And so you can see that there's 10 million ways to improve this, right? Like a better ODE solver has to do less steps, so it does less Newton's methods. Um, a Different methods for solving root finding equations could do this in a way that requires less calculations of the root finding function, or require the Jacobian or not require the Jacobian. And then better or worse methods for solving linear systems just allow you to do this more effectively. So, sparser matrix for the factorization, or smaller numbers of vectors that need to be computed. But this is why, there's so much research into stiff ODE solvers, because it's using all of this all together. And this is why for a homework problem, we're not going to build one. So just you could do neural ODEs on stiff ODEs, and this is something that we have implemented in DiffyQ Flux, and we'll see how you can treat this everything under the hood. We're not going to build this as part of the class because you can see this is a very complicated method. But if you're interested in following up on this, um, I specifically do a lot of work in stiff differential equation solving, so I can show you a lot of final projects you can do around new ways to be able to improve this. So there's ways to be able to directly use this inside of scientific machine learning, or there are ways to be able to incorporate neural networks into this process to actually make the solving of stiff ODEs even faster. So like that. In the next lecture, we're now going to be getting into how do you do parameter estimation of ODE problems, and how do you do reverse mode AD and solve neural and train neural ordinary differential equations, assuming that whatever ODE we're given is something that we know how to solve. Because now we've gone through, you know how to solve every ODE. Now, how do you find the parameters to match data?